Hello everyone, this video is going to briefly cover linear models but used for classification purposes as opposed to like linear regression, for example. All right, so just to sort of set the stage here, linear regression, the other type that we learned about, the more traditionally recognized one, is where we are trying to find a line of best fits to project or extrapolate out and see what future data might look like. Okay, this is different because we're doing classification. We're not picking uh, any continuous value or number that could correspond to new data, but rather, again, for classification, we're picking: are you class A or are you class B, class C, class D, right? These results are more discrete, if you will, and turns out we can actually use the similar linear models to do both classification but also this regression or extrapolation. So first thing you'll see up top here is this long equation that looks awfully similar to what we saw for linear regression, except the only difference this time around is that we have on the far right side, we have this greater than zero going on over here. Why is that there? Because instead of saying, let's say we got rid of this for a second, instead of just saying we have some amount of feature coefficients multiplied times some input data plus some kind of bias or offset or intercept, instead of saying all of that equals this value, we're actually defining a threshold such that when we cross that threshold over here, we will know that, okay, if you're above this threshold, you belong in this class, but if you're below this threshold, you belong in that class. Okay? So that's what's going to be different here. Do that. Okay, so like I mentioned right here, if you calculate a y hat value, you will see, zero is just an example threshold. Depending on your problem, it could be positive or negative. You could have, instead of zero, you could shift that out to be positive 5 or negative 7. It just depends on the problem. But zero is a good number that helps you understand because you have a positive class and a negative class. But that positive or negative is not indicative of any numbers associated with your data, but rather it just helps you make a distinguishment between you belong in this class or that class. Okay? So, because we're defining this threshold that we can be above or below, we're actually creating this thing called a decision boundary, to where if you fall above this decision boundary, then your fate is determined to be the blue class, or below it, you can be the red class. So let's get a little bit of colors on here. So for example, let's say we have data points that exist up here and data points that exist down here. Then this decision boundary, this is just an example of something our algorithm can learn. Hopefully this blue comes up pretty well. You can see that. I'll make it really thick here. But ideally, the algorithm that you're using to learn this decision boundary is going to look something like this, to where you can very clearly see where one class is and where the other class is. Okay? Let's go back a little bit. And depending on how your algorithm works and your regularization parameters and what your data looks like, this example I drew here with the red and green, it looks really simple, but you could have a lot more complex data. Let's try to add some more points in here. So something down here, actually go below a little bit, and have a little bit of green over in this region too. Okay? Now you might have a decision boundary that doesn't look as clean as this. I'll draw it in a lighter blue shade this time. You might get something that looks something like this, where you have members of both classes on either side of the line, but your decision boundary does the best it can to put as many of one class on one side and as many of the other class on the other side. But sometimes you have some casualties where there's a little bit of collateral damage where you have classes on both sides. So again, no algorithm is perfect, but as you work with this and experiment with it, you'll find that even though this classification doesn't get 100% of the classes right, it might just be accurate enough such that when new data is introduced, it can still classify it respectively well. Okay, this decision boundary is often called a hyperplane, especially when you're working with data in higher dimensions. The hyperplane, if you look at a 3D model of this decision boundary, because what I just drew here is essentially off of one maybe two features or features that you might have, right? But if you had data that it was 10 features or 15 features, you're more so forming a type of hyperplane, because 15 features, a decision boundary can't quite be represented on a 2D plane like I have drawn here. But there's plenty of examples of that out on the web. If I come across one, I'll be sure to share it. Okay, so one quick note here is that the learning methods, again, a lot of these concepts tie back to the linear regression that I talked about in other videos and that you may have seen in other resources. But the learning methods for these decision boundaries or these linear classification models will differ in two main ways. The first one is measuring how well a combination of your coefficients and your bias or offset fits the training data. Okay? Remember, in this equation here, the data that you start with is these points here, right? The parameters that we're learning are these ones over here, the W's and the B's. Right? These are your coefficients, this is your bias, and this is your feature input. Okay. So we're learning those parameters to see how well they will fit to the training data, right? Because if we get some respectable ability for these parameters, W and B, to fit to the training data, then we can use those to generalize and introduce new data and classify it with some level of confidence. The other way that our learning method will change in this case is the method of regularization. So a lot of different algorithms use regularization in order to have another aspect of the model that learns. It controls the coefficients a little bit tighter, such that you don't have you're less likely to overfit to the data, because you have this penalty term that punishes different coefficients if they get too controlling of your model. Right? If you have 20 features, you probably want your model to represent up to 20 features, close to it, maybe not exactly 20. But if you have 20 features, you probably don't want your model to work off of just 2 or 3 features. You probably want a little bit more information to go into the decisions that your model is going to make. Okay, so there's two major types of, or two popular types, I should say, of linear models that can be used for classification. That is logistic regression, logistic regression, and linear support vector machines, or SVMs. I won't talk about how these algorithms work. Those can be pretty mathy, and I want to keep this pretty high level, but just know that these are two popular types of models that are used in classification for linear models. Okay. Again, these both find a decision boundary to the training set. Their algorithms are a little bit different, but in the end, their goal is to learn this hyperplane or decision boundary that can be used to classify the data. So to give a really rough sketch of what that looks like, just so you get a picture in your mind, this is again the same old graph filled with a variety of data points. I'll pick another color here. Let's go with purple. So those are your data points. And again, both of these techniques here, logistic regression and linear SVMs, they're going to just learn a hyperplane. Let's say your logistic regression one looked like this, but your linear support vector machine might look something like this, right? They're learning hyperplanes. They're likely to be different. They're not guaranteed to be the same. But again, this is really what it boils down to. This is what we're trying to accomplish here. Okay, these classification models, they have this regularization parameter. We call it C. In the same way that our linear regression models used a regularization term called alpha, C is just the term that's used in these types. The equation changes a little bit, but just know that you're going to be modifying this parameter C just to use as a means of regularization on the model. And depending on how you change this value C, then you could be entering a trade-off between the, for colors, right, the importance of each point being classified correctly or the importance of generally classifying most points. What do those two bullet points mean? Well, let's say I put some data on this chart here. We're going to do the same thing that we did here. We'll just do different colors. We'll do orange, and we'll try to make them a little bit spread out and maybe have a bit fewer points. And change the color over here. Let's do a nice lime green. Okay. Now, we're looking at the importance of each point being classified correctly versus the importance of generally classifying most points. Let's start with that second one here. If we wanted to generally classify most points, actually I want to go with red here, then we can see, well, there's a lot of orange above, there's a lot of green below. So maybe if I just did my hyperplane something like this, right? There's a lot of green below, there's a lot of orange above. Generally, most points are classified correctly. And the reason I might want to do this is because, let's get a different color here. Let's go with blue. Let's say there's a green point here, green, 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 green. Let's say the average point is somewhere around here. And let's look at orange. Let's use purple here. We got orange, 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 orange. And let's say the average point of orange was somewhere around here. Okay? Now, why this is interesting is, what other color have I not used? Let's just go back to white. I might want the distance between purple to the red line and blue to the red line to be as big as possible. I want the average of blue to be as far away from this line as possible. And at the same time, I want purple to be as far away from this line as possible. And the reason for that is because if I want to be able to generalize to new data, then I want to be very confident that a purple class or purple data point is going to be classified as purple. And the same thing for green, right? The average point has a maximum distance. So the next time I get an orange class, the next time I get an orange point, it's very likely to be nowhere near close to that line, right? It could be really anywhere in this area because the further away that orange data points are from this line, the less likely that a new orange point that comes in is going to be classified incorrectly, right? And that works the same for the green side. Let's see this average down here. Let's say it was way down here. So the whole green class was just all the way towards the bottom of the page, right? And the average point was right here where I draw this X. Then the next data point that's similar to these green points is probably going to be way over here, which means that if the new data point is way down here, I'll probably classify it correctly just because there's virtually no chance that it'll even come close to crossing over this line. Okay? So if we want to generally, this goes back to this point here, since I've been rambling on for a little while, the importance of generally classifying most points right, we want to increase the distance away from this hyperplane, this red line here, such that when new points come in, we're pretty confident that they won't be misclassified. So now to cover the next point, let's just get rid of all of that. It's a lot of undoing to do, so we won't spend too much time on that. Okay, and we'll go back to white to draw our table once again, or our chart, sorry. Now we're looking at the importance of each point being classified correctly. So let's choose red data points. And let's do blue data points. Okay? If we were trying to do the same thing I just talked about, the general importance of classifying most points, the decision boundary might look a little something like, let's say, this here. Okay? Because the average blue is probably down here, the average red is probably up here. So the point, the distance away is pretty large, right? But you can see that we actually misclassified a couple blue points. And so, let's see if I can go back here. So now I want to focus on classifying each point correctly, right? I want all the reds on one side and all the blues on one side. So now my hyperplane might actually look like this. And so when learning this plane, I classify every point correctly. All the reds are above and all the blues are below. But you can see how close some of these points get to this line, right? So in this sense, you might think I'm overfitting the data because, you know, let's say I got a brand new blue point to come in. I guess this color right here. It could be right here. It could be right here, right? It only takes a small change in the data, a small variation in the data to make up the difference between this class over here and this class over here. So you can kind of see the trade-off that we're looking at here is that yes, we can classify all the data correctly, but ultimately, which choice is going to affect my ability to generalize to brand new data more? And that's part of the experiment that you want to have, something you want to be mindful of as you experiment with different algorithms and different decisions and hyperplanes and regularization parameters. So just be mindful of that as you explore these different hyperparameters that you will be toggling in your models. Okay. Now, another note I want to make here is that it's not always easy making this hyperplane. Again, the data, these two plots that I've made here basically represent one or two features, one or two dimensionality of data, right? And as you saw just now, that this blue point easily could have just crossed over and suddenly been in the wrong class, and now my model is no longer perfect, right? That's the challenge of making these hyperplanes, because in such a low dimensionality data set where you just have this one or two features, your hyperplane is literally just going to be a straight line across, right? It's going to be a line, a line, a line. It looks like a line, right? Why am I repeating that? Because in higher dimensionality data sets, you may no longer have a line, but you may have something that looks like a parabola, right? These different bends and curves, these low points and high points, can fit to higher dimensionality data much better. You can imagine if I just introduce, let's see if I can go back some to just having these data points. Let's say my hyperplane looked a little bit something like this, right? It still classified everything correctly, and if I got that brand new blue point to come in, it might be above the x-axis, but it's still classified correctly. And so the point I'm making here is that these techniques, these logistic regression and SVMs, their strengths really show in the higher dimensionality data sets. And so if you are using them for data that has a lot of different features, then you can expect to see some gains in your prediction accuracies, whether it's testing or training data. So again, quick summary to send off here. The main parameters of linear models is that regularization parameter. For these classifying models, That parameter is C, and you can move it up or down, typically in factors of 10, like zero point 0.1 or 1 or 10 or 100 or 1000. That's usually how you'll modify. That's kind of where you get the logistic part of logistic regression in some cases. But C is that parameter that you're using to find the best fit of your data. In regression models, like we talked about in a previous video, that term is alpha. They're both used for regularization. They both act as penalties to your features or to your weight matrix, your feature matrix, your coefficients, and your bias, such that it's another metric that your model can learn off of. And one last thing here is that, when you're making these machine learning models, there's a lot of decisions and assumptions that you might have to make about the model and as well as the data. And one other thing that I really didn't talk about much at all in this video is that we are using terms for regularization, but there's also different methods of adding regularization to the models. For example, you have this L1 or this L2. Remember, L1 is your lasso and L2 is your ridge regularization. So remember to take these tools with you, but also be mindful that it could be toggling one little thing in your model just to improve your accuracy. So with that said, I hope you learned something from this video. I hope it was useful, and I hope to see you around in a future video. Take care.